So what have we learned so far? We've learned that elements in the column behave alike because they have the same valence electron configurations, and that having full subshells like noble gases is extra stable. Hence, elements tend to gain, lose, or share electrons to obtain noble gas configuration. Metal elements tend to lose electrons when they react, and non-metal elements tend to gain electrons when they react. We also talked about the periodic trends. As you go up and to the right, the strength of electrostatic attraction between the outer electron and nucleus increases, and so the size of the atoms decrease. The ionization energy increases, electron affinity increases, electronegativity increases. And so the elements on the top right want to gain electrons, and the elements on the bottom left are more likely to lose electrons. They have lower ionization energies. It's easier to rip off electrons. And so that's consistent with the elements in blue being nonmetals. They tend to react by gaining electrons, and the ones in red being metals, they tend to react by losing electrons. The ones in yellow are metalloids, and they have behavior somewhere in between a metal and a nonmetal. And so the halogens, if they gain one electron, they get noble gas configuration, so they tend to form -1 ions. Oxygen, sulfur, if they gain 2, they get noble gas configuration, and so they tend to form -2 ions. The alkali metals, if they lose 1 electron, they get noble gas configuration, so they tend to form +1 ions. And the alkaline earths, if they lose 2, they get noble gas configuration, and so they tend to form +2 ions. And so today I thought we'd talk about ionic solids. Ionic solids are some of the most common compounds that we interact with. For example, common table salt is just sodium chloride. It is an ionic solid. Ionic solids are important in geology. Calcium carbonate is commonly found in rocks around the world. Ionic solids are also important in biology. A modified form of hydroxyapatite composes large portions of bone and teeth material. What I want you to be able to do with this information is you should be able to write down the formula of an ionic solid given its name. You should be able to describe why ionic solids are relatively stable. You should be able to describe what the lattice enthalpy is, that the larger the lattice enthalpy, the higher the melting point. You should be able to describe that the lattice enthalpy is due to the electrostatic attraction between ions. And given a series of ionic solids, you should be able to put them in order of increasing melting point and in order of increasing lattice enthalpy. And so metals tend to lose electrons forming positive ions, which are called cations, because their ionization energies are lower than nonmetals. Nonmetal elements tend to gain electrons forming negative ions, anions. They have more positive electron affinities typically than metals. Now the positive ions and negative ions can come together to form ionic solids. Now, to name positive ions, it's pretty simple. Typically, we just put ion after it. So the sodium ion is just called the sodium ion, potassium ion, magnesium ion, and calcium ion. Now, some metals can form more than one type of ion. And so iron can form a +2 or a +3. Now, to differentiate between the two, we use Roman numerals. And so the iron +2 is called iron 2. Iron +3 is called iron 3. Copper +1 is copper 1. Copper +2 is 2. Now, typically for transition metals, they can form multiple types of ions. And so we use the Roman numerals for the transition metals. Also for some of the P block metals like lead. Lead can typically form a +2 or +4. And so it use those Roman numerals. Now for the nonmetals, we have to change the ending. And so oxygen becomes oxide, sulfur becomes sulfide, fluorine becomes fluoride, and chlorine becomes chloride. Now, if you're going to write down the formula of ionic compound or name it, you always do the positive ion first and then the negative ion. And so sodium chloride, calcium chloride, magnesium sulfide. Now, one thing that's interesting to notice that the calcium chloride, you have 2 chloride ions for each calcium, but in the name it just says calcium chloride. Now the reason that we don't need to indicate it in the name is because calcium we know is an alkaline earth, should be a +2. Chloride ion is a -1. Ionic solids have no net charge. They're composed of charged ions, but the positive ions cancel the negative ions. And so because we know calcium should be a +2 and chloride a -1, that tells us there should be 2 chloride ions for each calcium ion. Now for FeCl2, we can't be sure what iron is because, again, it can form a +2 or +3. But if you have 2 chloride ions, that tells us that the iron here must be a +2 because, again, the positive ions and the negative ions have to add up to 0. Now, again, chloride is a halogen. It's going to form a -1 ion. And so you've got 3 -1, so that iron must be a +3. And again, if you're not sure about the charge, you use the Roman numerals. And so the charge on the iron can be determined by the number of chloride ions. The total charge on a compound has to be 0. And so again, the ionic compound is composed of positive charges and negative charges, but the net charge of an ionic compound has to be 0. And so again, for each iron 2+, you're going to need 2 chloride ions to get something neutral. For each iron 3+, you need 3 chloride ions to get something neutral. Ionic compounds are always charge neutral, and so the total charge has to add up to 0. So if you have a +2, you need 2 -1s to get to 0. Or if you have a -2, you need 2 +1s to get to 0. Or here for iron for iron oxide, we got 3 oxygen, each -2, so that gives us a -6. And so we need 2 iron 3+ to give us a +6 and to give us something neutral. And so we can figure out the formulas and names for the ionic compounds just by figuring out what's the ratio going to be to get something neutral. Now, sometimes you're going to use what's referred to as a polyatomic ion. And so an ionic compound can be composed of a metal ion and a nonmetal ion. Could be composed of polyatomic ion and a nonmetal ion, a metal ion and a polyatomic ion, or actually 2 polyatomic ions. Now, it's important that you actually know the polyatomic ions because, like knowing the elements, you'll see them, they stay together as a group. The polyatomic ions are fairly stable. And so I want you to know these polyatomic ions. They'll be used throughout the semester. Now, this list looks pretty bad, but as long as you know the trends, it's not that bad. And so the names are based on the relative number of oxygen. And so it always goes hypoite, ite, and then perate. Hypoite, ite, and then perate. And so perate has the most number of oxygen, then ate, then ite, then hypoite. Now notice that some you have 4 members of a group, and sometimes you only have 2. And so if there's only 2 members of a group, then it's just itonate, itonate, itonate. And again, one of the most confusing parts is it's the relative number of oxygen. And so the phosphite has 3 oxygen, phosphate 4, sulfite 3, sulfate 4, but nitrite 2, nitrate 3. It's also interesting, notice that changing number of oxygen doesn't change the charge. So all 4 of these chloride compounds have a -1 charge. All these 4 with a bromine have a -1. These 2 with the phosphorus have -3. The 2 with the sulfur have a -2. And so again, as long as you remember how the rules of naming it, you start with hypoite, ite, ate, and then perate, it's not that bad. Now, if you add a hydrogen, then you just put hydrogen in front. So you go from phosphate to hydrogen phosphate. If you add 2 hydrogens, then it's dihydrogen phosphate. But when you try to memorize the list of these polyatomic ions, make sure you don't forget the charge. And as long as you remember the rules, remembering the list is not that bad. And again, the polyatomic ions are important because they stay together as a group. So here we have ammonium chloride, and you have to be able to recognize, okay, this is the ammonium ion. And so when this dissolves, it's going to form the ammonium ion and the chloride ion. Magnesium nitrate, here you have the nitrate ion and magnesium. Iron phosphate, the iron ion, and the phosphate ion. Again, polyatomic ions are relatively stable, and so they stay together as a group. And so in your water, you probably have some phosphate, some nitrate, hopefully not some ammonium ion. Now for ionic solids, we always use what's referred to as the empirical formula. The empirical formula is the simplest whole number ratio of atoms in a compound. And so if you think about an ionic solid, this is a small thing for sodium nitrate. There's a huge lattice of different ions. And so it would be too complex to actually number how many ions you have. And so we just use the smallest whole number ratio. And so we'd call that sodium nitrate. But again, you're going to have a really large number of sodium ions and nitrate ions. So empirical formula, we always use empirical formula for ionic solids. Molecular formula shows the number each type of atom in a molecule. Structural formula actually shows you how the atoms in a molecule are bonded to each other. And so what is the chemical formula of the ionic compound that forms from potassium and bromine? Well, potassium is an alkali metal, so it's going to form +1. Bromine is a halogen, so it's going to form -1 ion. And so potassium bromide should just be a 1-to-1 ratio. Now, if we want to use a reaction to form potassium bromine, we'll start with the bromine liquid, which is a diatomic. And so if we have 2 bromine, we need to put a 2 in front of there. And if we put a 2 there, that means we have 2 potassium, and we need 2 potassium there. And so for each +1 potassium ion, we need a -1 bromide ion. So what is the chemical formula for ionic compound that forms from aluminum and bromine? And so bromine, we saw, was going to form a -1 bromide ion. Aluminum forms a +3. And so we would need 3 bromide ions for each aluminum. Now again, bromine is a diatomic. And so if we put a 3 here, that means we've got 6 bromide ions. Means we'd have to put a 2 there. And then if we put a 2 there, that means we have to put a 2 there. Again, so we want the product to be AlBr3, and the reactants are Br2 and aluminum. And then to balance it, that's what gives these coefficients in front. So for each aluminum, you'll need 3 bromide ions to make sure that the ionic compound is charge neutral.
Pieces of aluminum are cut from a strip of foil. Liquid bromine is placed on a watch glass and the pieces of aluminum are added. As the bromine evaporates, brown fumes are given off. At first, there is no reaction because of the protective oxide coating on the aluminum. An exothermic reaction between bromine and aluminum causes more brown fumes of bromine to be given off. White fumes are also given off.
So it's kind of a cool reaction. So what is the chemical formula of the ionic compound that forms from aluminum and chlorine? Well, chlorine is a halogen just like bromine. And so it's going to form a -1 ion. And so you'll need 3 chloride ions for each aluminum. Element in that center state for chlorine is Cl2. And so we'll put a 3 here, 2 there, and then we have to put a 2 there.
Aluminum foil is heated and placed in a flask containing chlorine gas. The aluminum reacts vigorously with the chlorine to form a cloud of aluminum chloride.
So how about sodium and chlorine? So sodium is an alkali metal, forms a +1 ion, chlorine halogen -1. And so we'll need a ratio of 1:1 for the sodium ions and chloride ions. And now again, chlorine gas is Cl2, so we'll have to put a 2 here. And if we put a 2 there, we have to put a 2 there.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
So a question you could see would be, what is the electron configuration of the ion that fluorine typically forms? And so fluorine is right here. It's a halogen. If it gains 1 electron, then it gets noble gas configuration of neon. And so the fluorine atom would be 1s2, 2s2, 2p5. The fluoride ion is 1s2, 2s2, 2p6. Which following is true? Ionic compounds are typically composed of a metal element and a non-metal element. And so that is true. But it could also be composed of a metal and a polyatomic ion, or a polyatomic ion and a non-metal, or 2 polyatomic ions. Ionic solids are held together by sharing and bonding electrons. This one's false. The ionic compound, it's held together by electrostatic attraction between opposite charged particles. What is the formula of the ionic solid composed of strontium ions and chloride ions? And so strontium is right there. It's an alkaline earth. And so it typically forms a +2. And then the chlorine, is a halogen, and it typically forms a -1. And so you need 2 chlorine atoms, chloride ions, for each strontium ion. Because remember, the ionic solid is composed of charged ions, but the ionic solid itself is charge neutral. And so this one's a little bit more difficult. What is the formula of the ionic solid formed from lithium ions and sulfite? And so lithium is alkali metal. It forms +1 ions. Now sulfite is on your list of polyatomic ions. And it's SO3 2-. And so we need 2 lithiums for every sulfite. And again, the polyatomic ions are important because they stay together as a group. And so as long as you're doing chemistry, you will see these.
Sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
And so the sodium loses an ion, forming the sodium ion. Remember, whenever you remove an electron, it gets smaller because you're reducing the amount of shielding. The chlorine gains an electron from the chloride ion. And whenever you add an electron, it gets bigger because you're increasing the amount of shielding. Now we can think about the energetics of forming sodium chloride by starting with the elements in their standard state. And so elements in their standard state just means typically how you find the elements by themselves. So sodium is a metal and chlorine is a gas. Now again, we can think about how we'd make the sodium chloride. Now, it doesn't actually occur in this manner, but we can get the energetics right. And so we can imagine, now also remember that the higher the potential energy, the less stable, the lower the energy, the more stable, just like when we talked about electron orbitals. And so say we want to go from sodium metal, sodium gas, so that's vaporizing it. You would have to add some heat, add some energy. And then say we want to break the chlorine-chlorine bond. So we went from the chlorine diatomic to single chlorine atoms. Now, we're going to have to form ions, so let's remove an electron from the sodium. And so it's the ionization energy for the sodium. And remember, it always takes energy to remove an electron. Ionization energy is always positive. Now we can add that electron to the chlorine. Now it's going from something less stable to something more stable. Remember, that's the electron affinity. And electron affinity is typically positive. Now we got the sodium ions and chloride ions in the gas phase, and we need them in the solid. Now in the gas phase, we can imagine that there's a lot of space between them, and so they're not really interacting. But in the solid, you're going to have strong ion-ion interaction. And so going from the gas phase to the solid, the only difference here is the ion-ion interaction of the sodium and chloride ions in the solid. And so the reason the ionic solids form is because of the ion-ion interaction, because of that electrostatic attraction. Now, this is referred to as last enthalpy. Last enthalpy is actually going from the solid to the gaseous ions, and it gives you a measure of the strength of the ion-ion interaction. Now, the last enthalpy is always positive. It always takes heat to go from the ionic solid to the gaseous ion. The stronger electrostatic attraction between the ions, the more stable solid and the larger the last enthalpy. Also larger the last enthalpy, the higher the melting point. Now, if you add up all these steps, we can see that there's a release of 429 kilojoules of heat if you went from the sodium metal plus chlorine gas to sodium chloride solid. Now again, this is not how sodium chloride is formed, but we can actually understand the energetics of the process. And so if the steps cause the amount of electrostatic attraction to decrease, it results in a higher potential energy. Again, the only difference between sodium ions and chloride ions in the gas phase and in the solid is that in the gas phase they're not interacting, so there's no ion-ion interaction. And so the stronger the attraction, the lower the energy, the more stable. And that's true if you're talking about ionic solids or if you're talking about electron orbitals. So what takes the most energy when forming an ionic solid? Well, typically it's the ionization of the metal. It's removing the ion for the metal. Why do ionic solids form? It's because of the ion-ion interaction. And so it's the measure of the last enthalpy. Remember, last enthalpy is a measure of the strength of the ion-ion interaction. And so we have a series of ionic solids, last enthalpy, melting point. And so typically the higher the last enthalpy, the higher the melting point. And the stronger the ion-ion interaction, the higher the last enthalpy, higher the melting point. And so remember, it just follows Coulomb's law. Force is equal to K, a constant we don't care about, charge particle 1, charge particle 2, divided by the distance squared. And so the stronger the attraction between the ions, the higher the last enthalpy, and the higher the melting point. Now, if we look at the numbers, it's pretty easy to figure out which one's going to have higher last enthalpy. So the most important consideration is charge, right? So magnesium oxide is a +2 and a -2. Sodium oxide is a +1, -2. And so magnesium oxide is composed of larger charges. The ones in green are all composed of a +1 and a -1. And so charge is the most important consideration. Now, after charge comes size. So the smaller the ions, the closer the ions, the stronger the interaction. And so sodium is smaller than potassium, and oxygen smaller than sulfur. And so the smaller, the closer, the stronger. The most important consideration is the absolute charge. So treat a +2 and a -2 the same. The larger the charge, the stronger the electrostatic attraction between the ions. The smaller the ions, the closer the ions, the stronger electrostatic attraction. Again, we're just following Coulomb's law. The stronger attraction, the larger the last enthalpy, the lower the potential energy, the higher the melting point, the more stable the solid, and the charge is the most important consideration. So a question you could see in very near future would be, put the following in order of increasing melting point. And so we first want to put it in order of charge. Again, just following Coulomb's law. And so sodium is a +1, oxygen -2, magnesium +2, oxygen -2, sodium +1, chloride -1, lithium +1, fluoride -1. And so magnesium oxide should have the largest interaction, highest melting point, because it's got the biggest charge, +2 and a -2. Now the lowest melting point is between sodium chloride and lithium fluoride. They're both +1, -1s. And the lithium and fluorine is going to be smaller than sodium chloride. And so the sodium chloride should have the lowest melting point, lowest lattice enthalpy. And so if we look at the actual numbers, magnesium oxide has a melting point of 2,527. For the ionic solids composed of +1 and -1 ions, it's 5 times smaller, 528 and 569. So ionic solids are rigid, have high melting points, high boiling points. Those that are soluble in water produce conducting solutions because the ions can conduct electricity in water. Which of the following is true? The larger the lattice enthalpy, the higher the melting point. That is true. Lattice enthalpy is just a measure of the strength of the ion-ion interaction. The stronger the attraction, the higher the melting point, the higher the lattice enthalpy. The bigger the charge of the ions in an ionic solid, typically the lower the melting point. That one's false. Typically the higher the melting point. And so when you're trying to figure out which has the highest melting point for ionic solids, first you look at the largest absolute charge. That's the most important consideration. And then after you do the charges, then you look at the size. The smaller, the closer, the stronger. So which of the following correctly lists the compounds in order of increasing lattice enthalpy? And again, so first we want to look at the charges. And so lithium is an alkali metal, so it forms +1. The chloride ion is a halogen, it's a -1. Cesium is also alkali metal, it's down there, so it's a +1. Bromine is also halogen, so it's a -1. Calcium is an alkaline earth, so it's a +2. Oxygen is a chalcogen, it's a -2. And so it tells us that the calcium oxide should have the highest lattice enthalpy, the highest melting point. Now the other two are both +1, -1. And so we can't do it in terms of charge, so we have to do it in terms of size. So lithium is smaller than cesium, and the chlorine smaller than the bromine. So that tells you the lithium chloride should be next, and then the cesium bromide should have the smallest last enthalpy and the lowest lowest melting point. And so again, higher melting point means larger last enthalpy. So this is a very similar question as last one. And so we have calcium, which is a +2, oxygen a -2. Magnesium is a +2, chloride is a -1, potassium is a +1, and bromide is a -1. And so for this one, we could do it just in terms of charges. So the calcium oxide has the biggest set of charges. And remember, it's the absolute size, so you treat a -2 and a +2 the same. Now the magnesium chloride would be next. Now we're not really worried about the two chlorines. What we're seeing is that, we got a +2 charge and -1. That +2 is bigger than if you have a +1 and a -1. And so then the KBr is going to have the lowest melting point, the lowest lattice enthalpy. And so that would be answer C. And it all started because atoms tend to get noble gas configuration by either losing, gaining, or sharing electrons. Elements tend to lose, non-metal elements tend to gain electrons. Now, we mentioned a while ago that for electronegativity, it's important because we can use it to determine the type of bond two atoms would form. One way of thinking about what forms on a compound, a metal plus a non-metal will form on a compound typically. Another way of looking at it is if the difference in electronegativity of two elements is greater than 2, then they tend to form an ionic compound. Lattice enthalpy is the energy difference between ions in the gas phase and in the solid. And so you can imagine it's a measure of the electrostatic attraction between the ions. The lattice enthalpy is larger when the charges are larger, the absolute value, and when the ions are smaller. And the larger the lattice enthalpy, the higher the melting point. So hopefully you can now write down the formula of an ionic solid given its name, or write down the name given its formula. You should be able to describe why ionic solids are relatively stable. Again, it's just the attraction between the ions. You should be able to describe that lattice enthalpy is. It's the energy required to go from the ionic solid to the gaseous ions. The larger lattice enthalpy, the higher the melting point. You should be able to put a series of ionic solids in order of increasing melting point or in order of increasing lattice enthalpy. Again, first you do the charges and then you do the size. I hope that helps.